Le premier orateur, c'est Leonardo Mazza, donc un régional de l'étape, qui va nous parler des fractional spin and statistics on quantum Hall quasi-particles. Merci, Lo. Oui.
Oui, c'est OK. C'est en anglais quand même, non? Yes, OK. OK, so yes, so thank you very much to everybody. OK, thank you very much to the directors, to Nicola for the nice introduction, but I guess thank you very much most sincerely to Raul and to Laura for putting together this beautiful program. I'm very much looking forward to the day, and I'm also very happy to have the possibility to speak here. Okay, so today I'm going to speak about my recent works on fractional spin and fractional statistics of quantum Hall quasi-particles. Yes. Okay, so okay, the big framework, the big picture of the talk of today is the fractional quantum Hall effect, a topic which is now 40 years old, so well established. I guess most of you know about it, so let me just spend one slide as a general introduction of it before entering into the main topic of my seminar. Okay, so what is it about? It's the physics of a two-dimensional electron gas in the presence of a very strong perpendicular magnetic field. Okay, so and the essence, or if you want, the strange things which have been observed in this system are related to the fact that I can apply a voltage bias around one direction, and I can measure the current in the perpendicular one. And here, this is the very famous picture, which is always showed whenever we discuss the fractional quantum Hall effect. Here on the x-axis, I'm plotting the magnetic field, and here the so-called transverse resistance or Hall resistance, which is supposed, if I apply a classical physics picture, to grow linearly with the magnetic field. But instead, when I actually go to low temperatures, deep in the quantum regime, you see that actually there are deviations with respect to this linear behavior, and there are little plateaus which establish different values of the magnetic field. Okay, so the physics of the quantum Hall effect, or the fractional quantum Hall effect, appears here. And now, I mean, since 40 years of work, actually, most of these, I mean, a lot of this has been understood. We have model wave functions, we have effective field theories, we have numerical simulations. I mean, a big bunch. We have also new theoretical concepts which have been developed to understand what is going on in these two-dimensional quantum setups. Okay, so what I'm interested in today are the excitations on top of this kind of systems. And actually, theorists have proposed and classified the two main kinds of excitations for this setup. I don't know where to place myself. Is it better? Okay, so gapless excitations which flow at the boundary, which are responsible for the current which is carried out in the system for this resistance, blah, blah, blah. And instead, gapped excitations which appear in the bulk. Okay, and these gapped excitations which appear in the bulk are indeed what I want to discuss today. So just to make it a little bit more concrete, I am showing here a numerical simulation of a fractional quantum Hall state. If I remember correctly, it's a Monte Carlo simulation of a Laughlin state. But as you can see, there are two quasi-holes which have been placed here in the bulk, where the density profile is more or less uniform. These excitations have a finite energy cost, and you can recognize that there are some quasi-particles here. Actually, here we call them quasi-holes because the density has been depleted away. Okay. It's the density profile of the gas. These are 200 electrons. It's a Monte Carlo simulation of a paradigmatic wave function, which we know. And I have discussed the wave function with two quasi-holes here, and you see that the density is depleted in a little region around that. Okay. There are also quasi-electrons where actually the density is accumulated in these regions. And these were proposed already by Laughlin, okay, so in 1983. The basics dates back to him, actually. What I want to claim and discuss today is that the quasi-particles which appear in the fractional quantum Hall effect fractionalize three quantum properties, and this is basically mainly the interest of these quasi-particles. Fractional charge, well known since the first studies by Laughlin. Fractional statistics, this was established a few years later by Wilczek, Arovas, so on. And actually something which is a little bit less known, also fractional angular momentum. And this is actually mainly what this talk is about, and the contribution I'm going to give to this topic. Okay, but before I enter into the fractional angular momentum, let me start with a fast review about the other two. So fractional charge, okay, this is actually the simplest and the most well assessed. Basically, it's defined in terms of the difference of the new density profile around here with respect to the flat and homogeneous density profile when I don't have anything. Okay, and now if you make this integral, it's possible to do it theoretically, but also experimentally, it has been measured. I mean, this charge, which has been depleted here, is a fraction of the charge of the electron. Okay, so for instance, for a Laughlin, very famous, a Laughlin at filling factor 1/3, the missing charge here is 1/3 of the electric charge of the electron. Okay, so quasi-particle for me is a generic word which works, which is both the quasi-holes and the quasi-electrons. Quasi-electrons is when I have excess of charge.
Sure, but for quasi-electrons, this pattern doesn't work very well.
It works.
You agree?
Yeah, okay. Numerical simulations work, show also here fractional charge. Yes.
No, it doesn't work so well.
No, it works. It works.
Okay.
I mean, there are the numerical simulations performed in Oslo in the 90s, but for the charge, show already that the charge is fractionalized, and these things has been repeated by Eddie Ardon and collaborators in 2018, and they have numerical simulations of the quasi-electron charge, and it's plus 1/3. And then we have the fractional statistics, okay, which is defined. I'm going to elaborate a little bit more on that, but I want to say that the analytics here has been performed in 1984, okay, then the numerics also has been performed a little bit later. And very recently also we had experimental probes about these fractional statistics. 2020, there were experiments actually even at École Normale Supérieure in Paris. And it is defined in terms of the phase which is acquired by a quasi-particle when it's braided, it's moved around adiabatically around another one. Okay, but because this actually is extremely important subject for the topic, so let me actually dwell a little bit more into this and say that indeed, discussing these quasi-particles, we have to abandon completely the notion of statistics defined in terms of symmetry or antisymmetry of my wave function. And instead, we have to rebuild the notion of statistics based on the notion of adiabatic exchange of particles and adiabatic braiding of a particle around the other one. Okay, so now, the exchange phase, so the phase which I get when I exchange adiabatically one particle with the other one, is exactly what defines my quantum statistics. So for bosons, if I exchange two bosons, I get a plus, it's well known. For fermions, I get a minus. And now in 2 dimensions, it is possible to extend all of these notions also to other objects, to other statistics. We have abelian anyons, where if I exchange 2 abelian anyons, the wave function gets a phase here. But we also have non-abelian anyons, which is even more intriguing. When I fix the position of the 2 quasi-particles, the wave function is not completely determined. I have a vector of wave functions, or I have a spinor if you want. And then when I exchange all of them, I generalize the action of a phase, which is a unitary matrix. And this is getting extremely interesting because people like Kitaev and afterwards a lot of other ones propose that this unitary matrix could be used actually to implement quantum gates and quantum computers. And this is the field of topological quantum computation. Yeah, please.
Okay. So for abelian anyons or non-abelian anyons, it seems that psi cannot be defined as a single-valued function. It seems that it has to be a multiple.
These are, I mean, indeed, these are not real particles. So, I mean, for what we have them, these are emerging quasi-particles somehow, which for which then the wave function is not single-value defined. Yes. Now, the notion of statistics, I mean, the other thing which we typically teach to our students when we discuss statistics or quantum statistics is the existence of a so-called spin statistics theorem, which links the statistical properties to spin, okay? Because typically, if I want to say to a student whether a particle is a boson or a fermion, I tell him you should just look at its spin. If it is an integer spin, have a boson. If it is a half integer spin, it's a fermion. And in a nutshell, I mean, this is what we have actually in our three-dimensional space. In a nutshell, the spin statistics theorem is actually written down here, okay? So if you rotate a boson of 2 pi, you get a phase +1. And this is exactly the phase you get when you exchange two bosons. If you rotate a fermion of 2 pi, you get a phase -1 because there is a spin which is half integer. And this is exactly the phase which you get when you exchange two fermions, okay, in a nutshell. Now, for me, a discovery was actually that the spin statistics theorem exists also for anyons. And I'm not gonna give you a detailed and precise mathematical proof here. I'm just gonna give you an idea of why I can claim that there is a spin statistics theorem also in 2D for anyons. So for the definition of the spin of the anion, I have to look at the rotation properties of my anions, 2 pi rotation property of my anion, which is pictured here as a little smiley. If I rotate it of 2 pi, I get a phase in front. And looking at this phase, I can define a spin J, which is written encoded up here. So this defines my spin. If I instead look at the braiding phase, which is the statistics, I move one particle adiabatically around the other one, as it is done here. And now what I get in front now is the braiding phase. Now the spin statistics theorem tells me that these two phases are linked, and the link is the following. Now you take the two particles like this, and now you imagine to rotate rigidly the global thing. I mean, I cannot do it. Now if I rotate rigidly the two things, you see that by rotating it, one is going around the other one, okay? The only difference with respect to this situation is that now I'm also rotating each single particle by 2 pi by itself. So if I subtract the fact that this thing has been rotating by itself and this thing also has been rotating around itself, I find actually the spin statistics theorem in this 2D, I mean, derived with hands, where I say that the statistical phase is equal to the spin of the composite of the two of them times the contribution of rotation of each of them rotated in the other direction. Okay, so now this actually is the spin statistics theorem for anyons, and the question I want to pose today is the following. So the quasi-particles of the fractional quantum Hall effect have a fractional statistics. This we know since 1984. The question is whether this particle also have a fractional spin that satisfies the spin statistics relation. Okay, this is the problem which I want to discuss. Sorry?
You just told us that this is a
Yes,
theorem.
It's a very good question. It actually allows me to comment on a very interesting point. So the theorem applies for anion developed as a let's say theoretical object, theoretical concept. But for me, the theorem is like the Pythagoras theorem in Euclid's geometry. Then it comes to constructing a building and checking whether this actually works when I look at real life. And this is the quantum Hall effect. Can I really apply all of this theoretical machinery to discuss this? Of course, it's natural to expect that, but there will be surprises, as you will see. Okay, so bear with me. So the talk is this. I will discuss this idea of the fractional spin. Then, because there are a bit of surprises, I will review a little bit of history and literature on this, and then I draw my conclusion because it will be late, I guess. Now, let me start with a statement of the main statement of the talk, which is, yes, indeed, it is possible to define a measure, even a measurable quasi-particle spin for the quantum Hall effect, the spin which satisfies this property, and the definition is written here. You see, I have here, I am looking again at a wave function like this. I create once more a little quasi-Hall here, and I define again what we technically call the depletion density. So the difference between the density of my system here and with respect to the homogeneous configuration where nothing happens. And now, instead of just computing the zeroth momentum, just the charge, the quantity, I compute the second moment of the distribution, the R-squared moment. Now this, I claim, is the spin of my quasi-Halls, and I claim that this satisfies the spin statistics relation, as I'm going to show. In fact, there is a reason, first reason why I think this should be reasonable. It is reasonable to do this. And the reason is the following. If you look at this and you focus on the lowest Landau level, Okay, we are indeed here working in the lowest Landau level. This expression is the expression for the LZ angular momentum. In the lowest Landau level, the LZ angular momentum is defined in terms of densities. And this is the expectation value of the angular momentum Z component for this depletion density, which I have defined here. Now I want to clarify, to avoid confusion in the following. This is unrelated to the spin 1/2 of the electrons. Okay, this works also for spinless fermions. This is not a SU2 spin of the electron. This is an emergent property of this quasi-particle, which is an emergent property of these hundreds of electrons, which I have plugged there. Okay, so what I'm going to do now, first of all, I'm going to give you an explicit value for this spin in some paradigmatic cases. Okay, I will give you a paradigmatic case of the Laughlin wave function, where we have also the analytical values. Then I'm going to anticipate to you, but I'm not going to discuss that this works also in the Halperin wave function, which is very useful, for instance, for discussing graphene and fractional quantum Hall effect. And then I will give actually some information about the Moore-Reed wave function, which is the simplest wave function which supports non-abelian enums. Okay, abelian enums for the Laughlin wave function, non-abelian enums for the Moore-Reed. Now, Laughlin. Yes, please.
I miss what is the definition of JC here.
Yes, you're right. I'm going to give it. JC is this. Let me. Can you bear with me?
Okay.
It's
okay.
the next slide. So the Laughlin wave function is written here. It's proportional to this famous formula Zi minus Zj to the power of m, and the m is related to the filling. Typically, for fermions we take actually m odd. For bosons we take m even. We consider a bit of everything. And then the expression of the quasi-Hall is written here. I have placed here Q quasi-Halls at the position eta. I can place 1, which is typically what we teach in classes, but I could also place 2, 3, 4, 5, as many as I want. Q is an integer here. Now, for the quasi-Halls of the Laughlin wave function, sorry. Okay, Zi. These are the positions in the two-dimensional plane of my electrons. Zi are really quantum variables, okay? And here you should consider of order hundreds of thousands if you can simulate that. Instead, eta is the position of my emerging quasi-Halls, and this is of order unity, let's say. There should be, I mean, this is the emerging property which emerges into this quantum liquid correlated quantum liquid.
So when you say that, when you say that you simulate that wave function, what do you mean?
Yes, this wave function, it's of course, I mean, there are two, I mean, it is possible to make numerical simulations of some observable properties of this wave function. The simplest is the density profile of this wave function. And typically to do that, we exploit the fact that the square modulus of this is actually related to the expectation value of the two-dimensional classical plasma, okay, with logarithmic interactions. And this actually allows you, since it is the observable you want, it's mapped on a two-dimensional classical gas property, then you do, at finite temperature, you do Monte Carlo simulations, and you simulate the density profile. That is how I actually showed you, we computed the density profiles. But now we also have more advanced techniques, like matrix product states and so on. Now, claim the analytical expression for this JQ, for the expectation value of this, for the spin of Q quasi-Halls, is this one. It's minus Q squared over 2m plus Q over 2. So there is a part which is quadratic in Q and a part which is linear in Q. Okay. I'm not going to give you the analytical proof, but I'm happy to explain you if you're interested afterwards. I'm just telling you that in the article we also have that. And the spin statistics theorem, just to show you, is this. Now you ask me what is the J of the composite. In this case, the J of the composite is the J of the two quasi-Halls, one on top of each other. Okay. So to compute the braiding phase, I have to subtract minus J2, which is the spin of the composite, plus 2 times J1, so the spin of 1. Now, with a little bit of calculations, you see that actually I can substitute this formula inside here, and I can get very easily to the final formula where the braiding phase is exponential 2 pi I divided by m. And now here you have the very famous exponential fractional phase fractional statistical phase, which was derived in 1984 by Wilczek, Arovas, and Schrieffer.
Excuse me. Yes, I have again the same question. You have here, it's a quasi-Hall wave function. Would you be able to do the same thing if you will use a quasi-particle wave function?
Yes, this is a great question, and this is what we want to do. But we have to do that. So we are in touch with Eddie Ardon, who has the numerics for that. And I expect now that the teaching is over to dedicate myself to that. But indeed, it will be extremely good because there have been difficulties in doing simulations for the statistics of quasi-electrons. Now, instead of showing you the analytical proof, I just want to give to you some results, some numerical results here. So here I am considering several values of m equal to 2, m equal to 4 for boson, and m equal to 3 for fermions. And here I'm computing the spin as an integral. Capital R is the radius of the region where I am performing the integral of the second moment. Okay, and you see that if I take a region which is large enough, all of these values saturate, apart from this, because actually the numerics becomes particularly difficult. Here, this is in black dashed line, you have the formula for the specific cases, the value of the formula for the specific cases, and you see that our simulations are completely consistent with all of these cases. Even here, where we are not able to get to saturated values, somehow you see that it's actually compatible with the expected values. Okay, so for the laughing, everything is fine, which brings us actually to a new method, if you want the crucial formula, I call it, a new method for defining the braiding phase of quasi-holes. So what do you have to do? Instead of doing interferometry, you could think of measuring it in a different way. You can place one quasi-hole in the origin, or you can place two quasi-holes at the origin. You can compute the depletion density, which in some sense you might be able to do. It's a measurable, observable. And you could just compute the second momentum, of this difference between the depletion density of two quasi-holes minus 2 times the depletion density of one quasi-hole. Okay. So in principle, you could actually extract information about the statistics just by taking a picture of your gas, which for me opens the way of actually detecting this in different setups with respect to those where this has been done so far. I don't know, for instance, in cold atoms, these kind of measurements are possible. Fluids of light, okay, that is also possible. And I believe maybe that would be interesting also to explore in graphene, where, as I understand, you could also do STM in the fractional quantum Hall regime. Now, let me maybe, how much time do I have?
10 minutes.
I have 10 minutes. Okay, then I can explain also this.
But question should also
It's almost done. Okay, or maybe let me just comment on this very fast. This is the Moore-Reid wave function, is another function where the quasi-holes, as you see, also written as eta. I have two quasi-holes here, eta 1 and eta 2. Now, there is this strange result here, which has some deep reasons, but let's just sketch it very fast, is that depending on the parity of the number of electrons or bosons, which I consider Z, the two quasi-holes have different statistical properties. Okay, this is, so if you want, in a nutshell, non-abelian anyons in the simplest example. And the braiding phase, which has been computed in this article, yes, I have two quasi-holes and I have a gas with, we said, the thousands of atoms, of electrons, or whatever you want. Now, the statistics, the fractional statistics of these two quasi-holes depends on the parity of the number of electrons which I consider. Okay. And indeed, the statistical phase is written here is 1/4m minus 1/8. And then there is a contribution given by the party, either 0 or 1. Okay. And we have done that. Okay. Here, for instance, I'm considering the case of boson, capital M equal to 1, which appears here. If I do this for even number of particles, I have a statistical phase which should be pi times 0.125. For odd number of particles, it's the same value plus 1/2. And you see here that the numerical simulations are consistent with this difference, with this. So the method is really robust and apparently works also for wave functions which are more complicated than just the laughing wave function, which is where somehow we test everything whenever we work the fractional quantum wave. Now, this actually brings me to the second and final conclusive part of the talk. And the question is, why did anybody think about this? Okay, because like I said, it's now 40 years of quantum Hall effect. And what I explained to you looks extremely simple and elegant. And we know that the brightest minds have worked on this. So how comes that in 2022, we can discuss this as a novelty? Now, indeed, people knew about this. So let me, for instance, show you this paper, 1995. Okay, so the fractional quantum effect was still a relatively young subject. These people were discussing a quantum Hall effect, and they were interested in a fractional spin. Indeed, if you look at this, it's written here. These quasi-holes have fractional charge, should be written somewhere here. They support, voilà, fractional charge, the first one, then fractional statistics, and then they write, we are concerned with a third fractional quantum number, the fractional angular momentum or spin. Okay, so the problem was well known to these people, which wanted a fractional angular momentum compatible with the spin statistics theorem. Now, 27 years later, this review appeared last year, and you can see that the notion, I mean, it's written by people who have done the study of quantum Hall effect, Feldman and Halperin, and you see that actually it's fractional charge and fractional statistics. So the notion has gone completely lost. Okay. So there is no mention in all of this review about fractional spin, not even commenting on the properties of it. So what has happened? Why? And now the reason is that people looked for it, but didn't find it. And it's a bit strange to see. Actually, I think everything dates back to this paper, 1992, where the authors were interested in the spin statistics relation and proposed this notion of spin. If you look at this, I then discovered this is exactly the formula I wrote for you. But because they didn't perform any Monte Carlo simulation, but I applied some plasma analogy and some rules for that, the constant screening sum rule, they get to the relation, they get to the result that this formula should be equal to 0. And then they write explicitly that this function yields a definition of spin that is they fail to yield the definition of spin that is in agreement with the spin statistics relation. So 1992, this somehow is, and then it's written inside that all the other authors who have worked on this agree on this conclusion. I mean, there is no spin. They say, apparently it should appear, but it doesn't appear. It's 0. Let's say what. Then Linus, who has invented the notion of anyons, says, I mean, this is too tricky. I don't believe that. There is an article who is published in 1991, never cited, where he says, I actually find it too strange. He says, I think the definition of spin should be this, and he writes once more our formula. And then he says, I feel that this should give a relation which is consistent with statistics. And so I asked a student to do Monte Carlo simulations. The preliminary encouraging calculations exist, they write, but they have never been published. And so the story, as far as I can tell, ends up here, and that's it. Now, just to wrap up, what is the situation of fractional spin now? So I have the impression that the notion of spin statistics theorem, in a sense, has gone almost completely lost. Okay, it doesn't. I mean, it's not discussed extensively in the literature, and we are kind of revitalizing it since years. But spin has been discussed meanwhile. Okay, it has been discussed in the framework of CFT. Okay, that exists. And it has been discussed because all of these people have computed it when you define a fractional quantum Hall effect on a curved surface, for instance, on a sphere. There they have been able to compute it, but they always write, if you then pass to the plane, it is 0. Okay, and the idea of the quadrupolar momentum of the annealing charge, I mean, we found in a CFT paper, I'm calling it, but it's actually a paper by Wigman. It's mentioned as a curiosity that there is a quadrupolar momentum which is related to the spin, to the CFT spin, as I understand. Not an expert about that. But I have the impression that things remained a little, I mean, it's written in the appendix E at the end of a paper of hundreds of pages, so it's not adaptive. So if I can say, I think we have kind of linked once more the quadrupolar momentum of this density profile to spin and to statistics somehow. And with this, I would like to conclude somehow saying that, yeah, so the quasi-particle excitation of the fractional quantum Hall effect, fractionalize charge statistics and angular momentum, and obey a spin statistics theorem. Of course, there are a lot of interesting things to do. First of all, we have to continue checking whether this is generally true. There is discussion about the quantization of the spin, which should be addressed extensively. I mean, fractionalization of angular momentum might be also related to strange angular properties. And then we have also to extend all of this outside the lowest Landau level, where I don't have a notion of rotation, which is as easily defined. I want to acknowledge the people with whom I have done this work. Okay, so Tommaso Comparin, Alvin Oppler, Elia Macaluso, Alexis Polychronakos, and Jacopo Carusotto. These are the people with whom I have discussed these ideas. And I would like to conclude, maybe, if you give me a second, advertising the fact that we are organizing a leader workshop in June, from the 7th to the 9th of June in Cergy, on the quantum many-body physics in the prism of an environment. So registrations are open. If you're interested, just subscribe. Thank you very much, Leo.
Are there some questions?
So thank you for the talk. Suppose I only have access to the cylinder geometry, maybe because I'm doing MPS simulations. Yes. So can I use some of these ideas?
Yes, definitely, because one thing which is a bit technical, but I did not highlight, is that this quantity which I have written is actually gauge invariant. So typically in the cylinder, you do MPS and you work with the Landau gauge. You produce your quasi-particle, and then if you extract the density profile, you should get the same density profile, and you should get the same.
One doesn't have to be on a disk.
Exactly, yes, but it should be, I mean, yes, in any case, I guess in terms of curvature is the same thing, because it's still without intrinsic curvature. So and in fact, that is something we want to try to do, because would be nice also yeah, I mean, we know that matrix Polar states are actually kind of versatile for doing this. And thank you.
Other question? Maybe I have one. If you go back to your slide 10, I remember you define the angular momentum of one quasi-particle as this integral.
Yes.
And so if you extend your, so it's connected to a small domain, but large compared to the size of the quasi. And if you include both, do you get the composite?
Not well. One has to be careful about that. So first of all, it has to be large with respect to the quasi-hole, but not so large that you see the boundary. Okay, because then it's spurious. If you get both, since it's R-squared, it's possible to extract the composite, I believe, but honestly, I don't know. I don't know. I should do the calculations.
Okay.
I should check.
Okay. No.
I would just wanted to know if it is experimentally observable or it can be done.
Yes, so it is I mean, this depletion density is in principle a measurable quantity. At least at the theoretical level, there is nothing, it's an observable, right? Now, the question is, can you do it? I have, for what I understand, that people who do fractional quantum Hall effect in two-dimensional electron gases tell me that it is not possible to access directly with STM the density profile, because the sample is buried inside substrate materials, which do not allow you to get there. But as I understand, apparently graphene is completely different. And we also have a fractional quantum Hall effect there. It's a bit different, but it exists also in graphene. I think that is interesting to see if it could work in graphene. STM of graphene is done.
Okay.
Donc, merci encore, Leonardo.